for joining me. I'm glad to have you here. I want us to look at specific heat capacity of a substance by electrical methods. Now we have, in a situation where we have the heat being supplied by an electrical material, for example, an electrical heater, or if we use an electrical heater to supply heat to a material. Now, that material absorbs heat while the heater generates heat. Now, in other words, we can have that heat supplied by electrical heater is equal to heat gained or absorbed, heat gained by material, or heat gained by a substance. And of course, we have the heat gain, which is a Q. So we said heat supplied is equal to quantity of heat gained. They are the same thing, if I use gained or absorbed. In other words, we have a Q. Recall that Q is equal to MC delta theta. So in other words, we can now replace this here and replace it here. However, in this case, you have, since heat supplied by the heater is Q, now which is equal to Q is equal to MC delta theta, and at the same time we have Q is equal to IVT. So the heat supplied is IVT, heat gained by the material is Q is equal to MC delta theta. So we can equate these two. So if we equate these two, we say heat supplied is IVT is equal to MC delta theta, where I is the current, V is the potential difference or the voltage, T is the time, N on this side is the mass of the substance or mass of the material, C is the specific heat capacity of the material. Now, delta theta is the temperature change. So in other words, we can now have, so we have this as an equation 1. Or we can have power times time is equal to, and of course, power times time is IV is power. Time is still there, is MC delta theta, which is equation 2. From Ohm's law, we can always make substitutions regarding I and V. So we now have from Ohm's law, we can have that V is equal to IR. I itself is equal to V all over R. Now, assuming we call this equation star and call this double star, they can put this into this. So as if we put equation star into equation 1, we can have I, in place of V, we have IR multiplied by T is equal to MC delta theta, this side. Now, if we open this bracket, we have I squared RT is equal to MC delta theta. So we can have this as our equation 3. We can have it as our equation 3. Now, this one, we can bring it here. You substitute equation double star into this. If we substitute it, we are going to have that. So in place of I, if we put I there, we have V over R, now multiplied by V times T. which will give us V squared T all over R is equal to MC delta theta. We can call it equation 4. So these equations 1 to 4 can be used to calculate equations 1 to 4 can be used to calculate the quantity of heat supplied. Quantity of heat supplied. Quantity of heat supplied. Okay, now let us take 1 or 2 calculations involving 1, 2, 3, and then 4. At the same time, for if we have, this is a calorimeter. This calorimeter, of course, it has 2 knobs from which we can now connect it into an electrical supply. Now, if we connect it, remember it has a heating element inside. And this material, inside it, we have the calorimeter. And assuming we have water inside this material, and at the end of the day, we connect this into electrical supply. Once this is heated up, 3 things are involved here. Heat supplied by this heating element is equal to heat absorbed by the water, or heat gained by the water. We have water and we have the calorimeter. So 3 things. So in that case, if such occurs, we now calculate it by taking note of, so we say heat. So we said if note, if electricity is supplied, a material supplies electricity. We can now have that heat supplied by heater. Heat supplied by heater, electric heater, is equal to heat absorbed. Heat absorbed by the calorimeter plus heat absorbed by the content, which is water, plus heat absorbed by water. So this we are going to see some of the questions involving this. Now let us take the first one. Now the first question says, an electric current of 3 ampere flowing through an electric heating element of resistance 20 ohms embedded in 1000 grams of an oil raises the temperature of oil by 10 degrees Celsius in 10 seconds. What is the specific heat capacity of the liquid? Okay. From here, we can have an electric element of current. The current flowing is 3 ampere. The resistance is 20 ampere, 20 ohms. can convert it to kg by dividing by 1000. If you divide by 1000, we have the mass to be 1 kg. The next one is temperature change. The temperature change is given to be 10 degrees Celsius. Now, time taken so far is 10 seconds. Now, the question says, what is the specific heat capacity? Now, in calculating the specific heat capacity, C, we compare the equation, which of the equations has R, I, and the T. And of course, the second equation, which is I squared RT is equal to MC delta theta. So this is our equation. So heat supplied by the heater is equal to heat gained by the material, which is the oil. So we have if current is 3 squared times, get the value of R, which is 20, times time. Time is 10 seconds, equal to mass. The mass is 1 kg times C. The C is what we're looking for. Times the temperature change. The temperature change is 10 degrees Celsius. Having gotten this, we now continue. 3 squared is 9. 9 times 20 times 10 is equal to 1 times C times 10 degrees. 9 times 2 is 18, which is 180. 180 times 10 will give us 1,800 equal to 1 times C times 10, 10C. Let's see the subject. C will give us 1,800 all over 10 will give us what? 180 joules per kg per Kelvin. So that is our answer. Now remember, you can still choose to leave your mass in grams. If you leave your mass in grams, that means here will now be around, if you divide this by 1,000, it will be 0.180 joule per gram per Kelvin. That is what per, sorry, the answer is, say this one is in degrees Celsius, it will now be per degrees Celsius. Okay, now let us take the second question. Now the second question says, calculate the power rating of an immersion heater. Calculate the power rating of an immersion heater used for 10 minutes to increase the temperature of 10 kg of water by 15 Kelvin. So, solution, we have the power rating is what you are looking for, which is the power there. Now, the immersion heater was used for 10 minutes. T is 10 minutes. And of course, you can convert this into seconds by multiplying 60 seconds times 10 minutes, which will give us 600 seconds. The next one is water of 10 kg of water. Mass of water equals 10 kg. And the temperature change, delta theta, is 15 Kelvin. And we are looking for, so we have C. The C given to us, which is specific heat capacity of water, 4,200 joules per kg per Kelvin. Having these parameters given to us, we have which of the equations will take care of power, T, which is the time, and the other rest of them. Well, the second one, which is power, the equation 2, which is power times time is MC theta. The power there is what we are looking for. P times time. Time is 10 minutes, which is 600 seconds, equals mass is 10 times specific heat capacity 4,200 times the temperature change, and temperature change is 15, which will now give us 600P is equal to 10 times 4,200 will give us 42,000. 42,000 times 15. By calculation, it will give us 630,000. Now, making the subject, power will give us 630,000 all over 600. Now, these two zeros can take care of themselves. We'll leave it us with 6,300. 6,300 divided by 6. If you punch your calculator, you will have that P is 1,050 watts. So we can now say that the power rating of the device is 1,050 watts. Alright, so that is the second question. Now, let us take another one. This question says, a heating coil of resistance 20 ohms connected to a 220 volt source is used to boil a certain quantity of water in a container of heat capacity 100 joules per kg. Sorry, 100 joules per Kelvin for 2 minutes. If the initial temperature of water is 40 degrees Celsius, calculate the mass of water in the container. Here we have two things given to us there. They said specific heat capacity of water is 4,200 joules per kg per Kelvin. Assuming the boiling point of water is 100 degrees Celsius. So let us quickly look at how to solve this problem. So we have here on the boards, the first thing is to write out the parameters given to us. They said a heating coil of resistance. The resistance of the coil is 20 ohms. Connected to 200, so the V there is 220 volts. It's used to now the heat capacity there. The heat capacity, remember in our earlier videos, we discussed about heat capacity. I will still drop the link and the description down below. So take a look at the heat capacity there. So heat capacity there is given as 100 joule per kg. So per Kelvin. The time is 2 minutes. Remember, these 2 minutes can be converted, giving us 2 times 60, which is 120 seconds. Now, initial temperature, theta 1, theta I is 40 degrees Celsius. Mass of water is we are looking for the mass of water. Mass of water is what we are looking for. Now, specific heat capacity of water is 4,200 joules per kg per Kelvin. Assuming the boiling point, of course, this boiling point is final temperature. I mean, the final temperature of water is 100 degrees Celsius. Now, of course, we are apply this formula. Now, if we apply this formula, heat supplied by heater is equal to heat absorbed by the calorimeter and heat absorbed by water. Now, for that of calorimeter, remember we did heat capacity. So heat capacity is, for us to get it, you now have the heat capacity times the temperature change will give us this heat absorbed by the calorimeter. So we now have heat supplied by the heater is, we have V squared T all over R. This is heat supplied by the heater. Equals heat absorbed by the calorimeter is heat capacity, either you say heat capacity or space, heat capacity CP. We can still use CP here. So we have CP times temperature change plus that of water. That of water will give us MC delta theta, where you have mass of water, specific heat capacity of water. Then here will give us, for the temperature, we have theta F minus theta initial. The same thing is applicable to this one. So we can always change this one to the theta F minus theta initial. Having all these things, so we can now substitute to get our value. So V is 220 squared times time. Time is 120 all over R. R is given as 20 is equal to heat capacity given to us, which is CP, 100 times temperature change, final temperature minus initial temperature. Final temperature is the boiling point minus the initial temperature of the mixture, which is 40, plus mass of water. Mass of water is what we are looking for, times specific heat capacity of water, times 4,200, times the temperature change. The temperature change is, permit me to clean this please. Temperature change is final, 100 minus 40. So, we now have this. We move 20 squared. If we square 220, it will give us 48,400 times 120 all over 20 is equal to mass of water. So we have 100. This 100 minus 40 is 60. 60 times 100 is 6,000 plus mass of water. Mass of water times this. Let's take this one first. Inside here, it was 60. 60 times 4,200 times mass of water will give us everything will give us 252,000 MW. So at this point we can multiply the 48,400 times 120 divided by 20 will give us 290,400 is equal to 6,000 plus 2,000 plus 252,000 MW. So at this point we can collect like terms here. Collecting like terms, we shift this one here. We now have 290,400 minus 6,000 is equal to 252,000 MW. Now, if we subtract this from that, we have that subtraction, we have 284,400 is equal to 252,000 MW. We can make mass of water the subject. Mass of water will give us 284,400 all over 252,000. Now, mass of water will give us this one, these two will cancel out these two. We have, this is 2 here, please. So we now have 2,844 divided by 2,520. So if we do that division, we have that this is equal to 1.13 kilogram. Therefore, mass of water here is taken as 1.13 kg as mass of water. Okay. This is where we'll end the lesson today. Please do well to visit the previous videos, and then do not forget to hit the like button, subscribe to this channel, turn on the notification button so that anytime I drop new video, you will be alerted. Thank you very much.